My name is Vaughn Bell. I am the Group 1 lead for Experiment 5, which is the gas turbine / jet engine experiment. And the purpose of this lab is to gain an understanding of the turbogen gas turbine generation system, perform startup, restart, and shutdown of the turbine, demonstrate the variation of basic engine parameters under different load conditions such as throttle, like varying the throttle, and determine optimal operation systems settings for the SR30 gas turbine engine. And the background, so the way it works is it's very similar to that of a Brayton cycle, which is shown above in the top left and a little bit in the top right. And then these types of engines are typically used for electrical power generation, in nuclear power plants, etc. And strategic sensors are used to measure the operating conditions of the engine and the entire system. So here's kind of like an internal view of the jet engine with the air intake, compressor, engine housing, turbine, and then the free turbine back here as well with an electrical alternator. And then so in an ideal Brayton cycle, it's assumed to be adiabatic and isotropic for the entire system. And pressure drop, there's assumed to be pressure drops in heat addition and heat rejection stages. In the actual cycle, the compressor does more work than the ideal cycle, and the turbine produces less work. And there's also irreversibilities. There's certain things, like in the ideal cycle, where you can't go back because there's not 100% efficiency throughout the cycle. And then so here's a picture of one of the control panels. One is like a master switch. You gotta flip that on before anything could happen. 2 is an engine start. 3, that red button, that's kill switch. And 4 is a variable power lever. 5 is a load lever. 6 is the LCD auto start display. And then 7 is an inlet temp. 8 is engine rotational speed. 9 is the turbine rotational speed. And 10 through 13 are just a bunch of analog pressure indicators. So the theory for it, these are, shown here is that's a TS diagram for the Brayton cycle, and that is a PV diagram for the Brayton cycle. So to find the specific work in, it is just the work in over the mass, and then that ends up being the specific heat times the delta T from T1 to T2, and then the work out, same thing except it is from T3 to T4. And then the specific work for the free turbine that I showed you earlier is same thing but from T4 to T5. And then you can find the engine efficiency by doing 1 minus the Q out over Q in, which is just shown there. It should be just broken down to T4 minus T1 over T3 minus T2. And the Mach number shown here is just the velocity over speed of light, V over C. And then so for the procedure, you gotta run startup, operation, and shutdown of the turbogen system. Use the operator panel that I showed y'all earlier. Calibrate engine and generator to make sure the data is valid. Basically that just means make sure it gets to steady state, make sure your data is good before you log it. And then collect pressure versus time, temperature versus time, RPM versus time, and electrical performance data. And calculate specific work of the system at different stages. Find the thermodynamic efficiency, performance of the engine. By that, you need to find the volume flow rate of air into the compressor, mass flow rate of air in, and the Mach number of the flow. And then find the power specific fuel consumption as well. And so big thing for this lab is safety. It's a big old jet engine, it's loud, you can get hurt. So one of the most important things is proper PPE, long pants, safety goggles, ear protection is a must, closed-toe shoes, and then the caster wheels on the engine housing need to be locked before anything happens, before you even turn it on. And then you need to perform a visual inspection of the engine, make sure that everything looks good, the housing, the glass shield is closed, everything's done good, and the fuel and oil quantity of the engine itself need to be optimal levels. And any questions?